Okay, so today we'll start with BGR or Bandgap reference circuit. Okay, so this is what we are going to discuss today, and the need for this bandgap reference is something like we want a golden reference. Okay, so whenever we try to bias any kind of circuit, what we assume is there is a kind of constant I reference is what we generally assume, and then we start building it, right? So now what we supposed to do with this bandgap reference is that we want to build that such kind of circuit which is ideal in nature. Okay, now in order to do that, I need certain properties to be satisfied. The very first property is something known as like little dependency on my V supply, okay, and also a little dependency on the process parameters. And the third important property that is required is something known as well-defined. So these are the three major important properties that we have to satisfy in order to build this BGR. Okay, so what I really mean by the first point is that any fluctuation in my power supply or any battery that you feed in to a circuit, that should not disturb the reference voltage or reference current that we are trying to build it. Okay, and the second one is like we know that mu n COX, that is a generic parameter that we always try to work in, and that particular parameter should not get disturbed because we know that this process parameter, something like mu n, is generally dependent on the temperature. Okay, so now what we wanted to do though is that when we try to build this particular circuit by making use of transistors, and that we know that it is basically sensitive to temperature, and any variation in this would certainly cause some disturbance to my mu n, and in turn it disturbs my I reference, and we want such thing or such kind of effect to be as little as possible. Okay, and in the third category is something like as I said before in the previous second case, that we have to build the circuit by making use of transistors, and we know that these transistors are sensitive to temperature. So basically the process parameters or in general are sensitive to temperature. Now what we wanted to do is like first we need to understand what is the dependency, what is the relation that we have between the temperature and the transistor, and I want to create a circuit that is independent of this temperature. Okay, so let us try to first, what is the behavior of my structure or a transistor with respect to temperature, that we will study, and later on we'll use that in a way that we can try to build a temperature independent circuit. Okay, so these are the three major important conditions that we need to satisfy in order to build this bandgap reference voltage or reference current source. Clear? Now out of this, the first two we will try to discuss, and then later probably in the second class we will talk about this particular concept. That is the third point, that is trying to understand the behavior of my transistor with respect to temperature, and then later we will use those. So once I understand what is the behavior of it, then I can use that to build what is known as independent temperature reference voltage or reference circuit. Clear? So with that, I'm just going to combine these two part into the first category. That is I'm going to split this task as two major tasks. One is to try to understand what is known as supply independent biasing. Okay, now when I say supply independent biasing, is that we are trying to address this first requirement. Okay, so any supply variation should not disturb the reference circuit that I'm trying to build in. Okay, and the second task, as I said, is to try to first understand the definition of or try to understand the temperature dependency on the circuit. Okay, and then later we utilize, so once I understand the behavior of the circuit with respect to the temperature, then I'll be using that to create what is known as a temperature independent reference. Clear? So that would be the second task. So this is what we want to build in. Okay, so now when we try to do this particular task, we will be combining the supply independent onto this temperature independent circuit, and then that completes our BGR circuit. Clear? So first let us focus on this supply independent biasing circuit, and then later we'll just try to move on. So normally any circuit in general will be biased with some kind of I reference. Okay, so what I do is I will take a current mirror circuit and then I will try to bias it with an golden reference or an ideal reference current source. Okay, so the circuit is well known. I'm just trying to replicate it. Okay, so this is a circuit which is nothing but the current mirror. This entire part is going to be a current mirror, and this circuit has been biased with this I reference. Okay, and now if at all, if I assume that the value of lambda is equal to 0, then we could actually write that the relation between this I out or ID2 and ID3 with respect to I reference. Okay, so now let us try to build. Okay, so now let us try to realize this ideal current I reference. Okay, by making use of a simple resistor. Okay, so the most generic way to realize this I reference is by making use of a resistor, and when we try to do so, then this would obviously will create a current which is I reference. Okay, just because there is a potential difference between this VDD and this particular point. Okay, so whenever there is a potential difference across my resistor, obviously the current would start flowing, and due to which I am just assuming that this I have selected the resistor R1 suitably such that the required I reference is being generated through this device. Okay, and our task in this entire discussion is that this I reference should not depend on my V supply or any variation on my V supply. So that is what we will try to understand through this. Okay, so now in order to do so, let me try to represent the variation in my supply as something known as delta VDD. Okay, so when there is a variation, then how will I model this this M1 transistor, which is diode connected configuration, and I'm looking at a small signal. That's the reason why whenever there is a variation in my supply, how will I model this particular M1 transistor? What type of impedance that it poses? Yeah, 1 by GM is nothing but is the small signal impedance, and that's the reason why I started with the discussion of when there is a small signal variation, what is happening, or how do I realize this entire circuit? Okay, so I know that this particular circuit or this particular diode connection could be generally modeled as something known as 1 by GM1 in parallel with RO1, and since because the value of lambda is assumed to be 0, so I can neglect this particular or not impact. Okay, so what I have is this one. So now once you have this, obviously when there is a change in my delta VDD, obviously this will also have some kind of change in my current. Okay, and this is what I want to model it. Clear? Now let us try to evaluate what is this current, what is the change in my reference current when there is a change in my reference supply. Okay, so how do you evaluate this particular thing? How do I evaluate this current? And you are actually modeling this entire circuit as something like series resistance R1 in series with 1 by GM1. So you know what is the variation that is happening here. Okay, and the only thing that I am asking is what is the change in my I reference current that is flowing through the circuit. So how do you evaluate that? Yeah, from here to here is what I am considering that resistance as 1 by GM. Okay, yeah. So if you have a voltage, how do you get a current? It's a simple Ohm's law, right? So V equals to I into R, and what I really require here is an I. So we just have to have V by R in order to get the current, right? So this V that I am talking is the small signal. So that's the reason why I just put this delta VDD, and that is, this change is actually causing a change in the current I reference. Okay, and that is what is flowing. So I can evaluate that to be equal to something like this. Okay, so now clearly the expression that I have here has a strong dependency on this delta VDD. Okay, so when there is a change in my VDD, there is a change in my reference current, and that is not what we actually wanted. Our intention is to make sure that somehow we want to break this relation. There is any change in my VDD, I should not have any kind of change in my reference current source, and that is my ultimate aim. Okay, so now what we do is we will try to postulate something. Okay, So the postulation okay, so to arrive at a circuit that is less sensitive to the change in my VDD, I'm just going to postulate some rule, okay. The postulation is something like the circuit must bias by itself, okay. So I'll just tell you what is this exactly it is, okay. So here in this case the I reference is basically is being derived through this VDD, okay, or something like a potential difference across these the power supply and the ground is actually trying to create this I reference, okay, and that is where somehow it has been related to my VDD. When there is a change in my supply, this is in turn creating a change in my reference current, okay. So somehow we have to break this rule, and I have to make sure that this I reference, rather than depending on this VDD, I want to try to generate out of the circuit itself, okay. So the circuit seems to be pretty simple. So by itself, what I really mean is I want to generate this I reference, okay. So now this particular circuit, how will I define this I out? What is the relation between this I out and I reference that I can write it? It's a current meter circuit. Okay, so it is something known as the aspect ratio of M2 output transistor divided by the aspect ratio of the diode connected transistor multiplied by this I reference should get me the value of the I out, right? So now what I really mean by the circuit that has to bias by itself is that somehow I want to have this I reference out of this I out itself, okay. So from I out I want to generate this I reference, okay, and that is known as the self-biasing circuit, clear? So let us try to, okay, can you imagine a circuit that could do this particular job? How did we generate I out basically? What was the input through which I generated this I out? The input is nothing but the I reference through which I generated this I out. I want to do the reverse engineering. I want to generate this I reference from the I out. Can you imagine a circuit that could possibly perform the same kind of operation? What is the circuit that I've used to generate this I out from the I reference? Current mirror circuit. Now how I can use that I out to generate this I reference, and what I really wanted is the circuit has to have the same kind of current directions, okay. So the I reference is flowing from VDD to all the way to the ground, even the I out is also following the same way. Now what type of structure that I can use such that from the I out I want to generate this I reference? Yeah, the same kind of current mirror circuit, but that current mirror has to be built by making use of is it a PMOS device or an NMOS? Yeah, so I have to rely on my PMOS device in order to have the same current direction, okay. So I don't want to change the current direction, but the thing is my ultimate aim is to somehow generate my I reference out of this I out, okay. So it's a pretty simple thing, but it's something like a circuit where I have this I reference that is coming as an output, okay, and the input, we know that the input has to be fed with some I out, okay, and I'm just generating that as an output as an I reference by making use of this M3 and M4 being built by making use of this PMOS structure. Now the bottom structure would remain the same, which is nothing but I'm using this I reference to generate my I out by making use of a diode connected NMOS, and I'm putting a diode connection just because the input current for this NMOS structure or this NMOS current mirror is I reference, and the output is my I out, okay. Is that clear? So this is my M1 and this is my M2, and this circuit is known as the self-biasing circuit, okay. Yeah, so first of all we will try to address one by one, okay. So this circuit in general will make sure that the I reference is generated out of my I out, and I out in general depends on my I reference. But there are a lot of flaws in this circuit. So first we'll talk about it, and later we'll talk about how to take it out. Okay, so that the output could be taken out when we discuss about the temperature independent reference. Okay, so till then we'll hold the circuit as it is, and we'll not discuss like how the current could be taken out. Okay, so with that we'll try to see. Okay, so what could possibly okay, so now let us assume that if I have this relation that my W by L of P is K times greater than the W by L of the other branch, then I can define, and even this particular NMOS is also having an aspect ratio which is K times greater than the W by L of the other structure. Okay, so through this entire structure what I have is an aspect ratio of just WP and so W by L of P and W by L of N, whereas the other structure has K times, and this factor of K could be either greater than or less than 1, or it can be equal to 1, or it can be even greater than 1. We are not worried about this particular thing. The only thing is I want to derive the relation of I out in terms of I reference based on this structure. So what would be the relation that we would get when I have K factor that is appearing on my M2 and M4 transistor? What is the relation that I share between this I out and the I reference? The same thing. The only thing is I can make use of this bottom structure alone and I can derive it. Okay, so the same way that we did before. N times that of I reference. Okay. So clearly I have some K factor, and through this K factor I can make as a kind of ratio between the I out and I reference. Clear? So let me talk about the issues that we have. Okay. So one of the major important issue here is what is the value of this I reference, or what is the value of I out I have? I don't have any control over it, right? So it is something like when a current is flowing, this current when it tries to flow, it creates an appropriate VGS, and that VGS is being copied here, and this in turn will try to create this I reference, and this I reference when it flows here, this in turn generates the corresponding VGS, and that has been applied. So it's a kind of loop that flows around, and it tries to maintain, or the circuit maintains the I out and I reference values as it is. Okay, that we know. So this circuit will do that job. But the point is, what is the exact value of my I out? There is no way by which it can be even equal to 1 microampere, or it can be even equal to 1 ampere. So we don't know what value we have for it. Okay, but we need some kind of control to have a particular value of current to flow across it. Okay, now in order to add this control, I'm just going to slightly modify this particular circuit. Okay, we know that this circuit works for all type of currents. It will work. Okay, the relation will hold for all type of currents. Okay, but the point is, like, I need some control to define a particular value of I out, and that is how we can design the circuit, right? Otherwise, any current, if it flows, then we cannot properly define what is the power dissipation of the entire circuit. I need a particular variable such that I can define what is the required amount of current that is to be sourced from this particular circuit. Okay, so to do so, I do two modification. Okay, one modification is trying to remove this factor K from M4 transistor, which means that when I try to remove this K factor, because the W by L of M3 and W by L of M4 are satisfying one or having the same aspect ratios, it defines me that my I out is exactly equal to my I reference. Do you all agree with it? Okay, so when I apply the first condition, this is what it defines for me. I'm going to apply the second condition. The second condition is by adding a resistor to the source terminal of my M2 transistor. So I'm just adding this RS as the source resistance. And now, having this as my total setup, these are the two modifications I've done. Let us see how does this in turn defines my I out as a variable of some factor K, and that is my ultimate aim. Or I can also try to vary the value of I out, or define the value of I out either in terms of factor K or in terms of the resistance RS. Okay, so I have two variables to control what type of current or what is the amount of current that I out has to have. Is that clear? So I need a variable to control a particular current to be generated out of the circuit, okay. And now I have two variables. One of the variable is the factor K, and the other variable is my resistance. Clear? So let us try to understand how does this happen. So what we do is, like, we know that the value of this VGS1 would be exactly equal to, how I can visualize this value of VGS1, how I can equate this VGS1 to the structure that I have onto my right. Can I write this VGS1 to be equal to, this voltage is copied across something else, right? Across which of the nodes it gets copied? I think the answer is pretty simple, right? So the VGS1 is being copied onto this VGS2, and across, right, this potential is connected here, and I have a ground, and I have a ground here. So obviously this VGS has to get split into two components. One is VGS2 plus my or the drop across my resistance, which I can normally write it as something like ID2 times that of RS, okay. And now what is the value of this ID2 right now according to our expression? When I have this M3 and M4 having the same aspect ratio, what is the definition of my ID2? What is this value of, so ID2 is nothing but I out, and this I out is nothing but equal to my I reference, okay. So now what I can do is, I can, since I want to derive an expression that is out of my I out, I will just replace this ID2 in terms of I out, okay, because it is the same current that flows, okay. And now I also want to replace this VGS and VGS1 as well as this VGS2 in terms of their corresponding currents, okay. Now while evaluating this VGS, I'm going to use this formula, that is, because I know that these transistors will be operating in the saturation region, and I'm going to assume that the value of lambda is completely equal to 0, okay. It's an ideal transistor. Based on this assumption, I can write the value of this VGS to be equal to square root of 2ID divided by Kn dash, and then the W by L of this N, okay. And also there is some, I have to add the factor of Vt of NMOS, okay. So that is the factor that I want to add in order to generate this VGS1 term, okay. Now the current ID that is flowing is basically I reference, and that is also will be equal to my I out. So I'm going to replace this ID1, okay, completely with this definition, which is basically equal to my I out, so that I will have across both the right hand side and the left hand side of my expression, everything is been defined in terms of I out, so that I can generate a term in terms of just I out, okay, and that is my ultimate aim. So I'll just try to remove this and then try to replace that with I out, because it's the same current. Just because of my M3 and M4 having the same aspect ratio, I would end up having the same current for I out as well as I reference, and due to which I can replace this ID1 with I out, clear? So similarly, I can also replace this VGS2 in terms of this I out itself, right? So which would be again the same thing, yeah, 2 I out divided by Kn dash, and the aspect ratio of this M2 is not the same as the aspect ratio of my M1, okay. There is a factor K that sits here, so I need to include that K times that of W by L of N, okay, plus the threshold voltage of 2, okay, which is basically an NMOS, so I'll just add this suffix N2, and along with it I also have this I out times that of RS, okay. So this is the total current that is flowing. Then now here I'm going to make an important assumption, okay. Until I do that assumption, I cannot solve this particular equation. The important assumption is that the body of this M2 transistor is basically is the same as that of the potential that I have across my source, okay, which means that the gamma is basically taken as 0, okay. So when gamma is equal to 0, then it means that there is no body effect, okay. Okay, so when gamma equal to 0, then it means that there is no body effect, and due to which the threshold voltage of my M1 and M2 transistor are going to be the same, and due to which I can cancel out these two terms. Okay, and now I'm just going to rearrange the terms such that I will have this I out times RS is nothing but 1 upon square root of k times that of 2I out by again kn dash the factor k w by L of n. Okay, now again what we wanted is this I out to be taken out, because I have both on my left hand side as well as on the right hand side I have this I out, and I want to bring it to one end and then try to obtain an expression which is having I out to be expressed as a kind of quantity in terms of the factor k and the factor RS. Okay, I forgot the factor RS here. Yeah, so yeah, it's sitting here, right? So I'm just going to make a square root on both the sides. Okay, sorry, taking square on both the sides. Okay, so when I do so, what happens is I would have something like I out square and RS square, and this factor would be retaining with the square value. Okay, and this entire square would go off, and I would have something like this. Okay, and now that what I can do is I can just cancel out one of the I outs from both the sides, and the I out could be returned as something like I out as okay. So now in this entire expression you could able to find that I have variables to control it. Okay, so what are the variables that I have to control the value of current I out? One of the variable is k won't be there. Okay, sorry, I forgot to eliminate that. Is that correct? Yeah, so hope that this is correct. Okay, yeah, so here in this case the definition of this I out is completely independent of my supply. Okay, and that is the very first thing, and that is what my main intention to do so. Okay, so the very first point is the I out expression basically is independent of VDD, and that is the first thing that I have to note. And I also have two variables, okay, that defines the value of I out. Okay, so whatever the value that you wanted to get out of the circuit, I can work out with these two variables. One of the variable is RS, the other variable is the K. Okay, so with these two variables I can define an appropriate reference current out of this particular circuit. Okay, yeah, so now this assumption is all valid just because of two reasons. Okay, two assumptions. One of the assumptions is I assume that the value of lambda is completely equal to 0, and that is the first assumption. Okay, and what are the other assumption that we have assumed is the factor gamma is basically 0. Okay, so with those two assumptions only I could be able to realize this particular circuit. Otherwise the feedback will not function properly. Okay, or I might not be able to have a circuit without these two assumptions, and and I will not get an expression I out which is completely independent of this R out and gamma factors. Okay, you can actually go through the textbook. There is one particular example problem that is given with having this lambda value that is not equal to 0, and then they have defined the same I out for the particular circuit, and the circuit is quite little bit changed. Okay, even that is an alternate representation of the same self-biasing circuit. Okay, I would advise you to go through that. Okay, so now let us see, is the circuit is completely satisfying all the relations that I have? There is again some sort of issue with this circuit. Forgot to write that. Forgot to write that. Okay, so the circuit, I can put it as a kind of drawback. Okay, so third is a drawback. The circuit it still depends on process parameter. okay, and that is one of the drawback that I could say. But there is also one more drawback that we need to consider, okay. The fourth or the second drawback that I have here is the circuit will also support one of the degenerative point, which means that it can also support I out to be equal to 0, okay. Yeah, so how do I justify this particular statement? It not only supports a properly defined value of this current, because I know that all of these factors in general will give me some positive quantity. So I have some value. So say let be as an example, this circuit can generate 1 microamperes of current, okay, and that is for sure. But the point is, this also has one more operating point where the I out is basically equal to 0. And how do I justify this relation? It not only have this 1 microamperes of current, but it also has one more operating point. So what I really mean is that there are 2 operating points for the circuit, okay, and the moment I turn on this particular supply, say for example, how do I turn on this particular device? So basically what we wanted is some kind of power supply. It could be either a battery or a switch, okay. So when I turn on this particular device, what happens is, like, the circuit, according to the equation that I have written, will also support an output current that is equal to 0, okay. If you have this I out to be equal to 0, because that satisfies this relation first of all, because both my I out and I reference will have the same value of current, okay, and that is the first quantity that I have. And when I plug in the same thing, this will also have to generate the same current, or this will, in short, it will end up having the same current of 0, okay. So this particular point, when I really turn on the device, the circuit in general gets into this particular operating point, okay, and this operating point we call it as a degenerate point. And I somehow want to come out of this particular, or I want to push this circuit or drive the circuit out of this degenerated point and try to switch over to this operating point, okay. So it is something like a monostable, okay. So the stable point is here, okay, or it could be a bistable, because even this is a stable. Once you put your circuit to get operated in that particular operating point, then still the circuit will function staying on this particular or generating this I out as it is, okay. The point is that in general the circuit will try to have a tendency to get into this operating point, and it's our duty to push this operating point from this I out being 0 to I out to whatever the value that you are trying to define with the factor K and RS. Is that clear? So we will not touch upon the circuit, because there is a circuit that is really required, but I'm telling you that this circuit is not completely the circuit is not complete, okay. So it also needs one more extra circuit, which we call it as a startup circuit, and that startup circuit will generally helps us to drive the circuit out of this degenerated operating point and pushes us to this an operating point where I define my I out to be this expression. Clear? Is the whole point is clear? The moment I turn on the circuit in general will have an I out that is equal to 0, and that is actually being satisfied even here, okay. So if I have 0, even my I reference is also basically equal to 0, and none of the transistors will be on, okay, the moment I turn on the device. So I have to make sure that these transistors are being turned on, and then once it turns on, then whatever the currents that are flowing is basically depends on this particular expression, okay. In order to do so, I have to add one more extra circuit, which we call it as a startup circuit, okay. So to eliminate or to drive the circuit out of degenerate operating point, we have to add what is known as a startup circuit, okay. So I will not specify what is that circuit. It is actually given as a part of your thing, but as far as syllabus is concerned, we are not going to discuss about the startup circuit, okay? But it's a very pretty simple circuit. There is a diode connected configuration that we need to add, but I will tell you what are there are two important properties that need to be satisfied by this particular startup circuit, okay? Means the moment I turn on the device, or the moment I turn on the supply, okay, this is at the moment at which I basically turn on the switch, okay. When the switch is on, the supply is on, and the startup circuit has to be on, okay. So, and this is one of the important property that I need to satisfy, okay. So this is one of the important property, and the moment it starts on, then it helps us to make these transistors, say for example there's M3, M1 and M4 and M5, to turn to saturation condition, okay. So this circuit, once it's on, helps the M1 to all the way to M4 to be on, and once these transistors are on, then the Iout, which was previously defined as 0 from this operating point, it goes to an operating point where the Iout is completely not equal to 0, or the expression that I gave in the previous page, okay. So it helps us to switch, okay. Once I switch on to this, where the Iout has been expressed as some kind of quantity which is not equal to 0, then this startup circuit has to turn off automatically, okay, and that is the most important property that I need to satisfy. So, and this is the second task it has to do, okay. So the startup circuit has to have it has two functions, okay. The first function is to self start by itself, okay. The moment I turn on my switch, it has to self start, or it has to be on by itself, and then once it attains these conditions, or once it satisfies these things, then it has to turn off automatically by itself, okay. So these are the two important tasks that the startup circuit has to have, okay. I will not go much in detail because again we have to satisfy some of the properties, and we will not discuss from here on, okay. So we will assume that there is a startup circuit, and that will perform these two operations, and with that we'll try to close this particular thing.